Hello everyone, this is the talk on the beeping model, and I will describe our new result where we show a lower bound on the noisy beeping model. This talk will have roughly 4 sections. In the first section, I will define the beeping model and the noisy beeping model. Then I'll state our main result, which like I said is a lower bound for the noisy beeping model. In the remaining 2 sections, I will prove this result by first describing the hard instance and then analyzing it. So let's start by defining the beeping model. What is the beeping model? The beeping model is a multi-party communication model where the parties are restricted to communicate only by sending and detecting signals. This means that in one round of the beeping model, the parties can either send a signal or not send a signal. I will denote the parties that are sending a signal by green and say that they beep a 1, and the parties that are not sending a signal by red and say that they beep a 0. Not only can the parties send these signals, but they can also detect whether a signal was sent by other parties over this channel. If none of the parties is sending any signal, then there is no signal over the channel and the parties can detect this. And in this case, I will say that the parties receive a 0. Similarly, if there are parties that are sending a signal over the channel, or there are parties that are beeping, or there are green parties, then there is a signal over the channel. And I will, in this case, say that the parties will receive a 1 and detect the signal. Okay, so this is the beeping model. Note that the symbol received, the Boolean value received by the parties, is exactly the OR of the values they beeped. If one of them was sending a signal, then the OR was 1 and they indeed receive a 1. If none of them were sending a signal, then the OR was 0 and they receive a 0. Why do we care about the beeping model? Well, we care about the beeping model because it is the simplest and the most fundamental model of communication possible. The theory here is that regardless of how an n-party communication model behaves, it should, at the very least, give the parties the power to send and detect signals over a shared channel. And this is exactly what the beeping model gives them. This beeping model is also found in several natural phenomena of interest. For example, you could have several biological cells in a common medium, and these cells cannot really talk to each other directly, but what they can do is they can secrete enzymes or chemicals into this common medium that the other cells can pick up and act based on them. Notice the parallel with the beeping model. There are parties that send signals onto a shared channel and the other parties detect those signals and act on them. Similarly, you could have several different models of nanorobots where the robots are so small that they cannot implement complicated communication protocols, but they can, at the very least, send and receive wireless signals onto a shared medium surrounding them. Okay, so the beeping model is great. It is simple, it is fundamental, it occurs in a lot of places of interest. But there is one feature that is present in all of these phenomena that is not present in our definition of the beeping model. And that feature is the presence of noise. In the cell case, for example, there may be the same enzyme secreted by a virus or a party that is not present in the system per se, or there may be enzymes that are not detected by the other parties. In the robot case, there may be wireless signals that are present due to the background noise, or there may be sometimes signals that are lost because the party was lost or its transmitter was broken. And both of these cases try to capture that in every natural phenomenon of interest, there's always room for noise, but it's not the case for our beeping model. So let's fix that by defining the noisy beeping model. In the noisy beeping model, we have the same phenomena as before. The parties can either beep a 0 or a 1, and the channel indeed computes the OR of all the beep values. But now, this time, what value is received by the parties may be different from the OR with probability epsilon. This means that with probability epsilon, the parties may receive the incorrect value of the OR. Here, the OR should be 0, but the parties are receiving 1. And it could also be the case that the OR is 1, but with probability epsilon, the parties receive a 0. This only happens with probability epsilon, and with probability 1 minus epsilon, the parties do receive the correct value of the OR. So now you have the beeping model, you have the noisy beeping model, and now a natural question to ask is, what is the relative power of the beeping model and the noisy beeping model? It is clear that because of the noise, the communication in the noisy beeping model is only slower than communication in the noiseless beeping model. And the question we are interested in is exactly how much slower is the communication in the noisy beeping model as compared to the channel when there's no noise. In this paper, we answer this question exactly, and we show that the presence of noise slows down the beeping channel by a factor of log n, where n is the number of parties in the beeping channel. Showing this result, which is an exact characterization of the effect of noise in the beeping channel, has two sub-theorems to it. In the first theorem, we need to show a communication task and a noiseless protocol for that task of some length t, such that any protocol over the noisy channel for the same task should have length t log n. So there is a log n separation between the two lengths. And then we need to show that no task can have more than a log n separation. Formally, that this log n factor is tight for all noiseless protocols of any length t. This lower bound, which is a separation of log n, is our main result, and it is the harder part. The upper bound is easy, although it's not entirely trivial because you need it to work for all lengths t, and this slowdown should be independent of t, even if t is like exponential in n or larger. But nonetheless, this is not our main result, and this is our main result where we show a task, a noiseless protocol for the task, and prove that any noisy protocol for the task should have length at least a log n factor more. And our proof of this result is actually much stronger than the statement. Our proof actually says that even if the noise is restricted to be one way, even if we assume that the noise in the noisy beeping channel can only convert zeros to ones, but it cannot affect ones. Even under this restricted noise, the length of any protocol for the task will be at least t log n. Okay. Curiously, this result is not symmetric. If you have a restriction for one-way noise that can only convert ones to zeros, then the theorem itself does not hold. And in fact, there is a way to simulate any task with only a constant slowdown. Again, I'm happy to answer questions on this, but I'll not go over this a lot. I'll only put these references here and focus on our main result, which is for 0 to 1 one-way noise, which is what we will consider throughout for the rest of this talk, only 0 to 1 one-way noise. There is a noiseless protocol for a communication task of length t. And for the same task, any noisy beeping protocol should have length at least t log n. So let's prove this. First, I need to define a communication task and a noiseless protocol for that task of length t. T will be 2n here. The communication task is the following function set. You have n parties in the beeping model. These n parties, n is 6 here, have as input a number in 2n. So they have an input, a number between 1 and 12. And they want to compute the set of all inputs to all the parties. In this case, they want to compute the set 1, 3, 5, 8, 10, which is the inputs that all the parties have. Okay, so how will the parties do it with the noiseless protocol? If there is no noise, I claim that there is a 2n round noiseless protocol, and the protocol proceeds as follows. In round I, for I in 2n, all the parties will beep if and only if they have the input I. For example, in the first round, the parties will beep if and only if their input is 1. So this party will be beeping and no other party will beep. Because there's a party beeping, the channel will give the value, and there is no noise, the channel will give the value 1 to all the parties, and they can include that 1 is in the set. In the next round, the parties will beep if and only if their input is 2. Here, none of the parties will beep. So the channel will give them the value 0, and they will know that 2 is not in the set. Similarly, in the third round, these two guys will be beeping, the OR will be 1, and the parties will know that 3 is in the set. And this will go on till round 12, which is round 2n, where the parties will beep, will not beep because they don't have the input 12, and they'll know that 12 is not in the output set. Notice here that this protocol only gives the set of all possible inputs to the parties. In other words, after this protocol, the parties know that all inputs are in this set, but they do not know that, for example, this party, what element in this set is the input for this party. This is not an artifact of this protocol. In fact, computing the set of inputs, determining which parties have what inputs in this set, is a hard problem. It requires at least n log n rounds. And this is because there are n parties, and each one of them has an input of length log n. So to determine these inputs exactly, or even approximately, requires at least n log n bits of communication. We'll use this fact later in our proof that a noisy protocol also requires n log n rounds. Okay, so this is our function set. This is the hard function. There is a 2n round noiseless protocol for the function set. And now I need to show you that any noisy protocol for the function set requires at least n log n rounds. The proof of this has 3 steps. And the first step is an observation about the function set. Here, I want to observe that the function set is such that change in the input of any of the parties is likely to change the output of the function set. For example, let us consider this party. The input of this party is 8. And now consider changes this input to any other value that is not 8. Regardless of what value you change this input to, the value 8 will no longer be in the output because none of the other parties have the input 8. And therefore, the output will be different. So regardless of what neighbor you go to, where by a neighbor, I mean a set of inputs that are different in the input of exactly one party. This means that because there are n parties and each party can have 2n inputs, there are like n square inputs. Regardless of which one of the n square neighbors you are in, for most of them, the output of set will probably be different. And because the output of set is different for most of them, the protocol must behave differently for an input versus its neighbors. Okay, this is the second step in our proof, observing that a protocol that computes set must distinguish an input from its neighbors. And the final step, which is the main step, is where we show that a short or less than n log n round protocol cannot distinguish an input from its neighbors well enough. Okay, so it remains to show this third step. And in this third step, I will consider rounds of the protocol based on the value that is received by the parties in that round. You can have rounds where the parties receive 0, or you can have rounds where the parties receive 1. And I'll show that either of these rounds cannot help the parties distinguish an input from its neighbors. For this, I will need to subdivide the one case into 3 subcases. And this is based on the source of the one. Because the channel has one way, 0 to 1 noise, a 1 can actually be a 0 that was flipped to a 1 due to noise. This will be our first case. Or the 1 can be without noise, which is these 2 cases. If the 1 is without noise, then indeed there were parties that were beeping a 1 in that round. And I will say there was a collision if the number of parties that were beeping a 1 is 2 or more. If 2 or more parties are beeping a 1, then these parties collide. There is a collision, and therefore the parties received a 1. Or you could have exactly one party beeping a 1, in which case I will say this is a 1 from an individual. So you have 4 types of rounds. You have rounds where you receive 0. You have rounds where you receive 1 due to noise. You have rounds where you receive 1 without noise but due to collisions. And you have rounds where you receive 1 from individuals. There is no subdivision in the 0 case because we assume that the noise is one way 0 to 1. So the zeros cannot be affected by noise. And therefore, this is only one case while there are 3 cases here. Okay, and now I wish to show that in either of these 4 cases, you have, in any of these 4 cases, the protocol cannot distinguish an input from its neighbors. Okay, so let's get rid of 2 easy cases first. And the first easy case is when the parties receive a 1 and this 1 is due to noise. I claim that a 1 due to noise cannot help the parties distinguish an input from its neighbors simply because the noise in the channel is independent of the input. Regardless of whether you are in the input case or in the neighbor case, the noise will behave exactly the same, and therefore you don't know whether, and therefore you have the exact same probability for receiving a 1 in this round. Okay, so the noise cannot help you distinguish. The second easy case is when the 1 is from collisions. Recall I said there is a collision if 2 or more parties deep to 1 in this round. Now, consider any neighboring input. In this neighboring input, I only changed the input for one of the parties. Initially, 2 of them were beeping a 1. I only changed the input for one of the parties, so one of them is still beeping a 1, and you will still receive a 1 in this round. So again, the protocol does not distinguish between the input and its neighbors, because in either case, you receive a 1 in this round. These were the 2 easy cases. Now I have the 2 harder cases for the zeros and the ones that are from individuals. Let's go over these. First, I'll go over the 0 case. And the high-level claim that I want to show in the 0 case is that even after you have considered all the zeros in the protocol, there is still a constant fraction of the parties. And for each party in this constant fraction, you still have root and neighbors that you haven't ruled out. Initially, you had n parties and n neighbors for each party. Now you have a constant fraction less, which doesn't really matter, it only affects the constants. But now you have root n neighbors at least for each of these constant fraction of the parties. And the property that I'll use in showing this claim is a property of one-way 0-to-1 error. This property basically says that because your error is one way, it can only change a 0 to a 1. If the parties are receiving a 0 in this round, they are sure that the correct value of the OR in this round is indeed a 0. Now, the OR in this round can only be a 0 if all the parties beeped a 0 in this round. And this means that any input for any of the parties that makes that party beep a 1 in this round is just ruled out entirely. It is not that the input becomes less likely or more likely slightly. It is just not possible because they beep a 1 in this round, the noise is one way, so they would have received a 1, but they instead receive a 0, so that input is just not possible. Now, suppose for the sake of contradiction that for many parties, you have less than root n neighbors remaining. In this case, for many parties, you know their input to within a set of square root n. Before the protocol, the input could have 2n values, but after you saw these zeros, you know the input to within a small set of square root n. And this reveals at least log n bits of information about the input. Now, if this is happening for many parties, then you receive an n log n bits of information about the party's inputs, which is not possible with less than n log n bits of communication. And therefore, even after you analyze all the zeros, there is a constant fraction of the parties with at least root n neighbors that haven't been ruled out. Okay, this is the guarantee that I wanted from the zeros. Now, there's one last case, which is the ones that are coming from individuals. These are the ones that are in rounds where exactly one person is beeping a 1, and therefore the channel gives a 1. After analyzing the zeros, I know that still there are a constant fraction of the parties that have root n neighbors remaining. And I claim that to rule out these root n neighbors for the constant fraction of the parties need at least n log n rounds with 1s. Why is that? Again, I'll use the property of one-way error, but this time I'll use a different property. In the 0 case, I use the fact that the zeros are too sharp. They make some inputs just impossible to happen. Here I will use that the one rounds are too weak, and they only affect the probability of inputs by a constant. Why is that? Well, if you receive, you can receive a 1 in 2 ways. Either the correct OR was a 1, in which case the one-way error will not change it, and you will receive a 1 with probability 1. Or the correct OR was a 0, in which case, because of the one-way error, it will go to 1 with constant probability, and you will receive a 1 with some constant probability. The difference or the ratio of the 2 cases is a constant. So a 1 round can only affect the probability of the inputs by a constant factor. Now, you still have root n neighbors for a lot of parties. And to rule out all these neighbors, you need to bring down the probability to below 1 over root n so that you can union bound. In one round for one party, you only lower it by a constant factor. So to bring it down to 1 over root n, you need log n rounds where that party is the individual party speaking a 1. Because you have many parties like this, you need log n different rounds for each party, because in each round, there's exactly one party that's speaking of one, and therefore these log n rounds for each party are disjoint. In total, you get n log n rounds of ones that are required to rule out root n neighbors for a constant fraction of the parties. And this means that the length of the protocol must be at least n log n. Okay, so let's summarize. We wanted to show a lower bound on the length of a noisy beeping protocol for the function set. We noticed that the function set is sensitive to a change in one of the inputs. So it changes from an input to its neighbors. Therefore, the protocol must also change from an input to its neighbors. And then we want to show that a short protocol cannot change that much. We had four cases. We had two cases first, zeros and ones, and we wanted to show that both of them cannot change that much. We divided this into three more, so now we have four cases. And we want to show that in each of these four cases, the protocol cannot change that much and cannot distinguish between an input from its neighbors. This was easy because a noise is just independent. This was easy because going to a neighbor in case of collision does not affect whether or not there is a one and beep or not. Here we use the fact that the noise for zeros is too strong and it rules out certain inputs entirely. And here we use the fact that noise is too weak and only affects by the probability by a constant factor. Overall, we get that, as desired, a noisy beeping model cannot have length less than log n and compute the function set. And this completes the proof and this talk. Thank you.